Imagine driving through a tunnel. Above you are millions of tons of water, and beneath your vehicle is a massive structure holding back the ocean. It sounds impossible, but engineers have built tunnels beneath rivers, seas, and ocean floors. So how do they do it? How can a machine dig through the ground while water is constantly trying to enter? The answer involves geology, pressure control, giant tunnel boring machines, reinforced concrete, and extremely precise engineering. Let's start with the biggest problem, water pressure. The deeper you go underwater, the greater the pressure becomes. And when a tunnel passes beneath the seabed, engineers have to deal with both the surrounding ground and the enormous weight of water above it. A small weakness can become a serious problem. That's why engineers don't simply start digging. Before construction begins, they study the ground. They use drilling, geological surveys, and other measurement techniques to understand the rock and soil beneath the seabed. They need to know where the ground is strong, where it is weak, where groundwater exists, and how different layers will behave during excavation, because hard rock behaves very differently from soft clay or water-saturated soil. Once engineers understand the geology, they can select the tunnel route and the correct construction method. And then comes one of the most impressive machines in modern engineering. The tunnel boring machine, or TBM. A TBM can be enormous. At its front is a giant rotating cutter head covered with cutting tools. The cutter head breaks the ground apart as the machine slowly moves forward. But an underwater TBM isn't simply a giant drill. It also has to control the pressure at the cutting face. Imagine digging a hole through wet sand. If you remove the material too quickly, the surrounding ground can collapse into the opening. Underground, the consequences can be much worse. Ground movement can damage structures, water can enter, and the tunnel can become unstable. So the TBM maintains carefully controlled conditions at the front of the machine. It removes material while supporting the surrounding ground. Behind the cutter head, another process begins, the tunnel lining. As the machine moves forward, it installs specially manufactured concrete segments behind it. These segments are produced with extremely precise dimensions. Mechanical arms place them into position. Several segments form a complete circular ring. Then the TBM moves forward again, and another ring is installed. The process continues for kilometers. Eventually, thousands of individual concrete pieces become one continuous tunnel structure. But concrete alone isn't enough. The biggest enemy is still water. That's why engineers use special seals and gaskets between the concrete segments. When the rings are assembled, these seals are compressed together to create a watertight barrier. Engineers can also inject material into the space between the tunnel lining and the surrounding ground. This helps stabilize the tunnel and reduce unwanted movement. So an underwater tunnel isn't simply a hole in the earth. It's a carefully engineered structure surrounded by multiple layers of protection. But once the tunnel is built, the engineering challenge isn't over, because now you have a completely enclosed environment. And that creates another major problem, ventilation. If it's a road tunnel, vehicles produce exhaust, people generate heat and carbon dioxide, and during an emergency, smoke can become extremely dangerous. Large ventilation systems are therefore installed to move fresh air through the tunnel and remove contaminated air. Long tunnels can require enormous ventilation infrastructure. And then there's fire safety. A fire inside a long underwater tunnel is much more complicated than a fire on an ordinary road. There may be no immediate escape to the surface. Smoke can spread rapidly. Emergency vehicles have limited space, and large numbers of people may need to evacuate. That's why modern tunnels can include emergency exits, fire-resistant materials, cameras, communication systems, and separate emergency passages. Some tunnel designs also use cross passages between parallel tunnel tubes. If one side becomes dangerous, people can move toward a safer section. Another critical system is drainage. Even a well-designed tunnel can experience small amounts of water infiltration. Instead of allowing that water to accumulate, Engineers build drainage channels and pumping systems. Water is collected and moved away. And critical tunnels may have backup pumps and backup power systems. This is part of a bigger engineering principle: redundancy. Don't depend on one system. If one pump fails, another should be available. If the main power supply disappears, backup power can activate. If one sensor fails, other sensors can continue monitoring. This becomes extremely important in critical infrastructure. The tunnel also has to deal with movement. The Earth isn't perfectly still, temperature changes, ground pressure changes, and in some regions, earthquakes can create additional forces. Engineers therefore use computer simulations to predict how the tunnel structure will respond to different conditions. They can model water pressure, ground movement, vehicle loads, temperature changes, and emergency situations. The deeper and longer the tunnel becomes, the more important these calculations are. But there's another fascinating fact about underwater tunnels. In many cases, engineers don't actually build the tunnel directly inside the water. Instead, the tunnel passes beneath the seabed. That means there is a layer of soil or rock between the tunnel and the ocean. This layer provides additional protection from the water above, but engineers still have to choose the correct depth. Going deeper can provide more protection. But it also makes construction more difficult. The tunnel becomes longer, ventilation becomes harder, emergency access becomes more complicated, and costs increase. So tunnel design is always a balance between safety, geology, construction difficulty, and cost. And then there's the TBM itself. A major tunnel boring machine can be extremely expensive and may be customized for the exact geology of a project. The cutter head can be designed for particular rock conditions. Pressure system can be adjusted for groundwater, and the entire machine may be assembled near the construction site before excavation begins. Once the machine starts moving, accuracy becomes critical. Imagine controlling a machine hundreds of meters long, deep underground, and making sure it stays precisely on its planned route. A small alignment error can become a major problem over several kilometers. Modern TBMs therefore use sophisticated navigation systems, lasers, gyroscopes, position sensors, surveying equipment, and computer-controlled steering. The machine constantly measures its position and makes tiny corrections. Those tiny corrections allow engineers to maintain accuracy over enormous distances. Eventually, two excavation paths may meet. This moment is known as a breakthrough. After months or years of excavation, two sections finally connect. But the tunnel still isn't ready for traffic. The interior has to be completed. Road surfaces or railway tracks are installed. Lighting is added. Ventilation systems are connected. Electrical equipment is installed. Emergency systems are tested. Cameras and sensors are activated. And every major system has to work together. Only after extensive testing can the tunnel finally open. And when it does, most people barely think about the engineering. They simply enter the tunnel, drive through, and continue their journey. But around them is an enormous engineered structure. Above them may be an entire ocean. Below them may be hundreds of meters of ground. And between those two worlds, a carefully designed tunnel is keeping water outside and people safe. That's what makes underwater tunnels so impressive. They combine structural engineering, geology, mechanical engineering, electrical systems, waterproofing, ventilation, and emergency technology into one enormous piece of infrastructure. And the technology will continue to improve. Future tunnel boring machines could become more automated. Robotic inspection systems could monitor tunnel walls continuously. Advanced sensors could detect tiny changes before they become serious problems. And air-assisted systems could help engineers predict maintenance needs. But the fundamental challenge will remain the same. Keep the ground stable, keep the water out, keep the structure strong, and keep people safe. So the next time you travel through a tunnel, remember what's happening around you. A giant machine once cut through the earth. Concrete rings were installed one by one. Seals were compressed to keep water outside. Pumps were installed to handle infiltration. Ventilation systems were designed to keep the air safe. and thousands of sensors and components were brought together to create a passage that looks simple from the inside. But behind that simple road is an enormous engineering achievement. If you enjoyed this engineering documentary, subscribe to the channel for more videos about mega projects, machines, infrastructure, energy, and the engineering that makes the impossible possible. Because sometimes, the most impressive engineering isn't above the surface. It's underneath it.